we are going to talk about antiderivatives and indefinite integration. This is also section 5.1 in your book, and much of it you'll be able to follow along with right in your book because I wanted you to be able to have two resources. Antiderivatives are exactly what they sound like. They're the opposite of a derivative. So if we are starting with knowing that f prime equals 0, and we want to go backwards and say what was the function that gave us f prime equals 0, what is it? So I want you to pause the video right now, and I want you to write down at least one, maybe two, and see if you can find, or if you can see the pattern. Write down all 8. All right, so I'm hoping you paused, and maybe one of your functions, sorry, I was going to write a capital F, one of your functions was at, say, 8. How about, was another possibility, I don't know, 0? The derivative of 0 is 0, the derivative of 8 is 0. How about f of x equals 1? How about, let's get creative here, f of x equals pi, or f of x equals 10.23. So basically, as long as you have a function that is a constant function, then your derivative is 0. So the corollary that's down here says functions with f prime of 0 are constant. The notation we use for antiderivatives is, this is the antiderivative of 0. So what gave me the derivative of 0? This tells us what variable we're talking about. We'll get more into that later. But any antiderivative of 0 is just some constant c, but we don't know. There are many options. There are lots. There are an infinite number, as a matter of fact. 8 is not enough. That's not, you can't contain it. There's an infinite number, because there's an infinite number of constant numbers. So how do we take that to the next? So list 8 functions that have f prime equals 9 as a derivative. Again, I want you to pause and write down at least one, maybe two, and maybe you'll see a pattern, and then we'll talk about that. So if you haven't gotten one, let me give you a little hint. How about f of x equals 9x, right? If you take the derivative using the power rule, you have 9 times 1, that's x to the first power, right? So 9 times 1 times x to the 0, x to the 0 is 1. So the derivative of 9x is, in fact, just 9. Okay, or think of it this way. Derivatives are slope. What's the slope of 9x? 9. Well, hopefully now you're thinking, oh, 9x, oopsie, plus 4. Or f of x could be 9x, wow, minus 10. Basically, it's got 9x in it, but then there's this extra thing at the end. So the antiderivative, if I want to go backwards and say, hey, if my derivative was 9, what did I start with? Well, I started with 9x plus some constant. So that's the antiderivative. It's actually not one antiderivative, it's a family of antiderivatives. Like we said on the last time, there's an infinite number of antiderivatives for the last one. There's an infinite number of antiderivatives for this one. That's what the plus c means. It's called the constant of integration. We'll write that down in a little bit, but it has a special name. And it just says, hey, it's 9x plus something. It could be some kind of vertical shift on the graph, right? So the slope's the same. It just shifts vertically. All right, so list 8 functions, and I know I haven't been listing 8. I see it being a little redundant. But list 8 functions that have f prime equals 2x as your derivative. Go ahead and pause and write at least one down. So what do you think? How about f of x equals x squared? That'd have a derivative of 2x, right? But kind of like the last ones, hopefully you're getting this pattern, f of x equals x squared plus maybe 3. Or f of x, I got a better pen, equals x squared minus pi. That would be 2x minus 0, right? And basically, if I'm taking the antiderivative of 2x, that just tells me my variable's x, with respect to x, then that's going to be x squared plus some constant number. So this antiderivative sign just says, hey, this is a derivative in here. What would I have had to have as my original function if that inside function there in the antiderivative is the function I got? It's my derivative I got with my original function. What's the original? So functions with the same derivative have a special relationship. All right, so functions that have the same derivative differ by a constant. So in other words, if you think about, let's look at, like, say this one. These two functions, now I didn't call them f and g, so let's call this one g for a second. This guy right here, I'm trying to look for my little highlighter, there we go. This guy right here, f of x, it's 9x plus 4. G of x is also 9x, but it's minus 10. It's off by negative 14. That c was negative 14. So in other words, if f prime equals g prime, like it did up in those two up above, they both have a derivative of 9, then f of x equals g of x plus some constant. Now keep in mind, just like above, that constant was negative, so that c can be a negative 14. All right, so let's kind of put all this together and use some calculus notation. So the definition of antiderivative, a function big F. Now we usually use big F for antiderivatives. We kind of used our notation on the other page that we were used to, but technically we usually use this big F for the antiderivatives, and I'll show you what I mean in a second. The antiderivative big F is an antiderivative, because we just said there's a lot. It's an antiderivative of F on some interval I if f prime, big F prime, equals f of x for all x in I. Okay? So if f is an antiderivative of f on some interval I, then g is an antiderivative of f on the interval I if and only if the antiderivative g is equal to the antiderivative f plus c, which is exactly what we wrote on the other page, just with a big F and a big G. And I do not know why they tend to switch them so that the F and the G are on opposite sides of the equal sign, but they do in this one. C, remember, is the constant of integration. This is the general antiderivative, it's called, for some solutions G prime, and C is called the constant of integration. So those are important terminology points. So if I'm taking the antiderivative of some f of x, you always put this dx at the end, it's called the differential. We tend to write it f of x plus c. So that's how we do it. Instead of writing a derivative in here, the antiderivative of a derivative, we tend to write it like this. The antiderivative of some little function gives me this original bigger function of f. And that's why they have different letters. So big F and little f are different things, and that's kind of a big effing deal. Ha ha ha. Okay, math joke. All right, so let's try to come up with some rules for antiderivatives like we did with derivatives, so we don't have to keep doing this. But we're going to kind of keep going back to that thought, like, hey, if I want to find the antiderivative of x, I have to say, hey, if this was my antiderivative, if that was my derivative, if I'm trying to find the antiderivative of it and go backwards, what did I originally start with? So hopefully you're like, okay, to get an x, I had to go down a degree. So I had to have started with an x squared, right? So it wasn't x squared, but that's not right. If I take the derivative of this, what do I get? It's 2x. So that wasn't right. That didn't give me an x as my derivative, but it's close. What if I change that by just putting a 1/2 out in front? What happens then? Now take the derivative of this guy. If I take the derivative of that, bring the 2 down, multiply it by the 1/2, you get your derivative that you care about. That is the derivative is x. So that is the antiderivative with one minor little thing. This is always forgotten. You've got to add this plus c. That is the constant of integration, because as you noticed in all those other ones, you could have plus 2, you could have plus 4, you could have plus pi, you could have plus 1,000. And it still gives you the derivative of x. So we're kind of having to think backwards on this one. If I have an f prime equals to 3x. So just to be clear, we're kind of doing these more like this. Oops, I forgot my differential. That's a grave tactical error. You'll do it too, and it is really important. You have to have it. AP gets really picky about that. Don't forget it. So I'm sorry, that prime just started to look really gross. So I'm making it more like the antiderivative of f prime dx. On this past page, we said the antiderivative of just little f equals big F. That's really the more appropriate notation. However, you can write it that way as well. And this is the way we're kind of thinking about it for these pages because that's what we're used to. So if I get a derivative of 3x squared, what did I start with? Well, I would have had an x to the third, right? And hey, that gives me my answer, right? If I take the derivative of this, that's 3x squared. Hey, good, okay, but don't forget, there's always that possibility that it's plus 12, plus 2, plus 8. You don't know. So this plus c has to be on it. The antiderivative is x cubed plus c. All right, now, what about if I were doing the antiderivative of x squared? So in other words, hey, if we got an f prime is x squared, what did I start with? Well, kind of like that first one on the last page, you would have had to start with an x cubed, right? But that gives you 3x squared when you take the derivative, so that's not quite right. We just need x squared. So you need a coefficient out in front. If I multiply 3 by 1/3, I get 1. And so then we get 1 x squared, which is what we wanted. So if I take the derivative of this guy right here, that's my original function. That would be my little f of x kind of. We're going to call him big F of x for future. That's really what you call most antiderivatives. But it's going to be 1/3 x cubed. But you also have this constant integration. You could have a plus 2, you could have a plus 1,000, you could have a plus pi, you don't know. Now, how about this next one? Now, I see I have a typo because, you know, it's Miss Kite and you can't have a thing without a typo. So that's actually a third. See, I copied it wrong. I cut and paste from above probably. All right, so if I'm supposed to get an x cubed as my answer, what did I start with? So I had to have an x to the fourth, right? Notice that the power is 1 up. But I have to have that 1/4 out in front to get rid of that. When I bring the 4 down, multiply it by a fourth, that makes 1 plus c. So if I have to go backwards, notice that I'm adding to the exponent every time. I add 1 to the exponent every time. And for these ones right here, I have to have that coefficient out front. Notice also that that coefficient is the same as that exponent. So if I'm going to come up with a general power rule for antiderivatives, if I want to take the antiderivative of some power, x polynomial type function, if I want to take the antiderivative, add 1 to the exponent, and divide, oops, sorry about that, and divide by that same coefficient. Don't forget your constant of integration. Now, this is the same as up here. I just want you to notice that that's the same thing as x to the fourth over 4, 1/4, plus c. So those are really equivalent. Same thing here. This is x to the third over 3 plus c as well. Now, that said, we're going to go on to our next video, and the next video will be about notation more than anything, and then just some general antiderivative rules, and then practicing taking some antiderivatives. All right, look forward to the second video.